Hello, welcome for another great installment of some AP Chemistry lectures by Mr. Lambert. This is the start of Unit 4, Chemical Reactions. You can see here the bookwork problems and these just gives the bookwork problems. Please see Google Classroom for the outline chapters. We've also posted the bookwork problems up there. Okay, so our first section, we're going to just a quick introduction to chemical reactions. Now, a lot of this is actually all we really need to talk about right now. A lot of this is a review from from last year or whenever you took honors chemistry. So, physical and chemical changes. Physical changes are changes that occur when a substance undergoes a change in its properties, but it's still the same substance. Okay, there's no change in composition. There's just a change in the properties. This could be a phase change. It could be when a mixture forms or separates, cutting something into smaller pieces, crumbling something up, changing something. If it's a piece of metal, we could draw it into wires or flatten it into sheets. These are all just physical changes. Changing its color by like simply painting it or something like that. These are physical changes. A chemical change is a change that occurs when a new substance is produced. Now, we have these four indicators of a chemical change that were discussed in honors chemistry. We have a production of energy. We have a formation of a gas, formation of a precipitate, and a color change. So, a production of energy, I should say, it could be either a use of energy or a production of energy. It should be a change in energy, whether it's endothermic or exothermic. And sometimes we see this just in heat, increase or decrease in temperature, and sometimes we see it in the form of it giving off light or a fire. Formation of a gas. Keep in mind things to look for when you see a formation of, or when you see a gas form. You might see bubbles coming out of the mixture. You may see or substance. You may see some sort of vapors coming off, something to that extent. Now, keep in mind when you have a phase change going from a liquid to a gas or a solid to a gas, there's a formation of a gas there, but we have to think, is a new substance being produced? And if it is a new substance, then it's a chemical change. But if it's just a physical change forming a gas, well, that's just a phase change. Formation of a precipitate. Remember with double replacement reactions, when you mix two solutions together, if it forms a precipitate, that is a solid forming from solution. That is the definition of a precipitate, when a solid forms from solution. You can also see this with a single replacement reaction. Not all single replacement reactions will form a precipitate if they will react. Sometimes that substance that a single replacement reaction produces could be a gas or a liquid in the case of something like bromine. So formation of a precipitate, a solid that forms from solution. And just keep in mind that not all mixtures of solutions will form a precipitate, which is something that we'll talk about in detail in another unit. Color change. You're also going to have a color change that occurs with most chemical reactions. Not always, but a color change. Now, just because you see or observe one of these four indicators doesn't mean we always have a chemical change. That's not what we're saying here, all right? Because it could very well be a physical change. But what you need to use these things for is another piece of evidence to prove that an observation that you would have to prove to back up your claim that a chemical change would occur. Okay, so the next section we're going to talk about is Ionic Equations. I'm actually we'll see how far we get in this video. I might actually talk about electrolytes and then pause and then go back and make a separate video about Ionic Equations, but we'll see. So electrolyte is a substance whose aqueous solutions contain ions. So you dissolve it and it produces ions. Okay, best example, sodium chloride. Any salt that as long as it will dissolve, will produce an electrolyte. Some other covalent compounds, when they dissolve, will produce ions as well. And typically these are substances that will produce acids. We'll talk about them as well. Now, these electrolytes are going to be able to conduct an electric current. Okay. Now, this says that there are three types of electrolytes. It's actually probably not written correctly. There are three categories. There's actually two types of electrolytes. It's either a strong electrolyte or a weak electrolyte. Now, strong electrolytes completely break apart into ions, whereas weak electrolytes partially break apart into ions. And so with a strong electrolyte, 100% of the particles that is there will be ions in the solution. With a weak electrolyte, some of the particles will be electrolytes, some of them will just be the actual molecule still intact. With non-electrolytes, that is a substance that stays in its molecular form. It's dissolved in the water, but stays in its molecular form. Strong electrolytes are going to be salts and strong acids and bases. Weak electrolytes will be any other acid or base. We call these weak acids and weak bases. And then non-electrolytes is everything else. A lot of organic substances are non-electrolytes. Sugars, alcohols, all these things are non-electrolytes. Okay, and we'll categorize them here in a little bit better. All right, so when ionic compounds dissolve, they're going to produce ions in water. So these ionic compounds, when I say salts, that's what we mean by ionic compounds. All right, think about those as being analogous. So each ion in that ionic compound, as it's dissolved, is going to be surrounded by water molecules like we learned about in the previous unit. Now, these ions, the movement of those ions is what is conducting that electric current, those actual ions. And so in order for something to conduct electricity, it has to move along some sort of charged particle. Now, typically with electricity, it moves through electrons, through a movement of electrons, but it can move through ions as well. Electricity, that is, can move through ions. And so that's what makes salt waters electrically conductive. Molecular compounds can ionize into solution, sometimes 100%, sometimes only partially. Other molecular compounds are not going to ionize in solution. And so it's actually a different term that we use here. Notice the use of the word notice the use of the word, let me just make sure I'm right. Notice for ionic compounds, notice the use of the word dissociate. You can think about this as the ions, when they're dissolving, they are ceasing to associate with one another. All right, they are dissociating. Okay, they're already ions, they're just dissociating. But when we come over here, when we're talking about molecular compounds that break apart into ions, we talk about ionize. We use the term ionize because molecular compounds are not ions in their molecular form. They're molecules. So when they dissolve and form ions, they have to first ionize before they can actually be in that solution. And so it's the end result is the same. It's just different uses of the term depending on the substance that we're talking about. So when we're talking about acids and bases, actually, technically, when we're talking about acids, we use the term ionize. And if we're talking about bases and salts, we would use the term dissociate. That's actually not always true now that I think about it. So when we're talking about most bases and salts, we would use the term dissociate. But for a base like NH3, we would actually use the term ionize. And we'll have to discuss that later when we talk about acids and bases. I'm not going to bring that into the fold now unless it's absolutely necessary later. Or you can ask me in class. And then you have other molecular compounds that are not going to split apart into ions. They're not going to conduct electricity, and these are your non-electrolytes. These are going to be the non-electrolytes. All right, so strong molecular compounds, really acids and bases, these are going to be either strong or weak. We'll go over the list later. And then molecular compounds that do not break apart into ions are your non-electrolytes. So let's look at this particle diagrams. I talked in class about how particle diagrams are really, really important piece. And so let's talk about what particle diagrams look for. Strong, weak, and non-electrolytes. Okay, so particle diagrams. So over here we have a strong electrolyte in NaCl. And we see that in the solution we have positive ions and negative ions broken apart. Okay, and just to be able to fit more in here, I made a little key down here of what my positive circles and negative circles were. But these Na pluses and these Cl1 minus, and now that I'm looking at it, I realize that I'm off by one. So let's just put another plus right down here because it does need to be even because it's a 1-to-1 ratio. So now I think I have 5 and wait. Did I not? You know what? I had enough. All right, well, let's go put a negative right there. Now I think we're good. Okay, so you have that implies that they're touching. So let me get that. See, look. So you have positive ions and negative ions completely broke apart in the solution surrounded by water molecules. Over here, we have a weak electrolyte. A weak electrolyte, HF is a weak acid. Yeah, and in that we have a weak electrolyte, and you'll notice that we have some HF particles, but then we have some H plus particles and F minus particles. Okay? And so you're going to have both species, F minus, F minus, F minus, H plus, H plus. I didn't purposefully do that. I probably should have put one in the other and put some in the top, some in the bottom. Let me evenly distribute them as best I could. Hard to do that, but these are acceptable. And again, I should show that they are separated. They are not touching. They really need a bigger piece of paper, write smaller to be able to do this correctly. But the whole idea is that you have the species that are present. You're going to have HF, you're going to have H plus, and you're also going to have F1 minus. All of those species present in the solution. Whereas over here, you only have Na plus and Cl minus. All right, and then lastly we see over here this is a non-electrolyte. All right, this is a non-electrolyte, and you're only going to see the for CO2 gas when it's dissolved. I should make it an AQ because now it's dissolved. So you see that you just have the CO2 particles. You do not have ions here. The only species present is CO2. Okay. Okay, so for strong electrolytes, when we're looking at strong electrolytes and showing an equation to represent this, what you're going to see here is you're going to see the strong electrolyte written on one side, aqueous, and then on the other side, you'll have, first of all, you'll have a one-sided arrow, and then you'll have H plus aqueous plus Cl1 minus aqueous. You have the ions with the aqueous because that's the physical state written after it. This is hydrochloric acid, ionizes when placed in water. So NaCl, on the other hand, well, actually, really same thing. You see the Na1 plus aqueous plus Cl1 minus aqueous when it's dissolved in water. This is the way that we would represent it when we're writing ionic equations. So, and notice because these are strong electrolytes, you're going to have that single forward arrow. All right, this implies that once the substance is placed in water, it exists exclusively as those ions. As opposed to weak electrolytes. Now, weak electrolytes, we're not going to show a one-sided arrow. You'll notice here right away that there's a double-sided arrow. That is implying that you're going to have this species present, this species present, this species present for the bottom one, and then up here you'll have this one, and this one present. All right, like I showed you in the particle-like diagram for HF. This is just two other weak electrolytes. So acetic acid is a weak electrolyte, and so you'll have that double-sided arrow. One side you'll have the molecule, the molecular compound, written as if it's still a molecule, which it is partially, and then you also have the ions that it would ionize into, but not 100%. Okay. All right. Yeah. And then lastly, we would have a non-electrolyte. We really wouldn't change anything here. We're going to take this liquid and you'll place it in water and it'll be dissolved to CH3 aqueous. You could have a situation, we just back up here. You could have a situation where you took, you said, all right, I got HCl gas, and that's the form that you would talk about, and you place it in water. All right, what are you going to get? Like if you're stating that I'm taking a gas and I'm placing it in water, all right, what are you going to, sometimes you might see, all right, let's put it in water, and then you'll have H plus aqueous and plus a Cl1 minus aqueous. You could have that written for the strong electrolytes, but it's important to note for the weak electrolytes, you need to have the aqueous here because it's implying that you have this species in the solution as well. Whereas here, you know, I've seen it written both ways where what we start with, or if you just see this. So what you start with, this is what you'd start with. Hydrogen chloric gas, for example, or NaCl solid. All right. Writing this, when you see this, you need to think this. All right. When you see a strong electrolyte written, the substance aqueous, you need to be thinking, oh, those ions are there. That's really what we mean when we write HCl aqueous. All right. Whereas opposed to if you see a weak electrolyte and it's written aqueous, you need to think, okay, that thing exists, the molecule, as well as the ions that will ionize it into. All right. And so you need to be thinking this in your head. Now, here in a minute, we're going to use all these when we do, and then non-electrolytes just, looks the same. It's just you're changing the physical state. Here, just giving you a few more substances. Hydrocarbons, alcohols, and sugars are non-electrolytes. So this actually helps you identify the strong electrolytes and weak electrolytes. So strong electrolytes are going to be all ionic compounds. None of the ionic compounds will be weak or non-electrolytes. Okay, and then molecular compounds that are strong electrolytes, you're going to have strong acids, which is table 4.2 in your notes. That's going to be H2SO4. You need to memorize these. HCl. HCl. Let me get away from that. HBr. HI. HNO3. HClO3, and HClO4. I believe that's right. All right, 7, 1, 2, 3, 4, 5, 6, 7. Yeah, so hydrochloric acid, chloric acid, and perchloric acid. All right. Okay, so those are your strong acids, and now for your now for your strong bases, because they're also going to be strong electrolytes too. And these are, all this is given in table 4.2, the list of strong acids as well as the strong bases. Your strong bases are going to be your group 1 hydroxides. All right, group 1 hydroxides, as well as calcium, strontium, and barium hydroxide. Okay, if you look on your periodic table, calcium, strontium, and barium hydroxide are the heaviest group 2 metals. So your group 1 hydroxides as well as your heaviest group 2 metals, calcium, strontium, and barium hydroxide. Okay, so this next slide here, we talk about how electrolytes can conduct an electric current. But let's talk specifically what we would see if we were to do this demonstration of this. With a strong electrolyte, which is what you see here in the middle, you would see a very bright bulb because you got all those ions in there and all those particles are able to conduct an electric current. With a weak electrolyte, you're still going to see the bulb light up. And I should just back up here. We got an electrical source, all right, and we got the negative N in the water and the positive N in water. This is completing the circuit to allow the bulb to light up, right? So when you put these metal plates in the water, if the water has some medium for the substance to conduct electricity, then you will light up the bulb. So that's what we see with a strong electrolyte. We see a bright bulb because there's lots of ions there to be able to conduct that electricity. Now with a weak electrolyte, we're still going to see the bulb light up, but it won't be as bright because we don't have as many ions there. And so you'll see the bulb light up, but it definitely won't be as bright. And we see acetic acid here, which is a weak acid, and I should have gone over that. So we have our list of strong acids here and our list of strong bases. Any other acid or base is going to be a weak base. Okay, so acetic acid is not on the list of strong acids, so it's a weak acid. And that's what we see here, acetic acid. All right, particle level diagram for it. A little bit deceiving because it's actually C2H3O2 1-, but hey. This is your molecules that are present, and here's your ions. It's just not as many ions to be able to conduct the electric current. And then over on the far left, we have ethanol, which is an alcohol, does not break apart into ions, does not light the bulb. So this is going to be your non-electrolyte. I'm going to stop here. I'm going to put all this together in one video, and then I'll make a separate one on how to do ionic and net ionic equations.